All right, so we're going to move into the last lesson of probability, which is probability models. And we'll talk about probability distribution models in particular. Some probability distribution models will look like this. It's for a discrete data set. We have a possible outcome of 5, 10, or 20 with the individual probabilities. This is another probability model for a discrete data set. And then we could have an infinite data set, and we will go back to talking about normal distributions and how normal distributions, we did use them as percentages. If we had area, we'd use percentages, but they also can mean probability. Since underneath the normal curve is 100%, well, 100% chance instead of just 100%, or instead of 16% of our population, we would say we have a 16% chance. Okay, so let's go right into it. Very quickly, it's a fairly simple lesson, at least for this first page. Second page will require a little bit of review of our normal distributions, which we'll do. So here's a probability distribution. We have values of 5, 10, and 20, which are just like outcomes, and they're probabilities. So 0.6, some blank, 0.1. And I ask you to find the missing probability. Well, with probabilities, we always add up to 1. Okay, the probability of the sample space, all the possible individual outcomes is 1. So if this is 0.6 and this is 0.1, that's 0.7. This middle has to be 0.3. Now they ask you, what is the probability of x, so your outcome being greater than 5? So it'd be the probability of 10 and 20 occurring. Well, we have a 3% chance of 10 occurring, a 30% chance of 10 occurring, and a 10% chance of 20 occurring. So we'd say this is a 40% chance, 0.4 or 40. What's the probability of x not being 10? Well, 30% chance of being 10, we could take 100 and subtract the probability of being 10, and we'd get the probability of not being 10, which would be 7 or 0.7 or 70%. Okay? So easy enough. All we need is our table. They add up to 100. We answer our questions using the table. Here's another situation, discrete data set. We have all human blood types can be typed as one of O, A, B, or AB. But the distribution of the type varies a bit with us. Here's the distribution of the blood types of a randomly chosen Black American. So the distribution varies based on the race, and this is talking about a Black American. We have that 49% is chance of being O type, 27% chance of being an A type, 20% chance of being a B type. Now, what is the probability of the AB blood? Well, all of these have to add up to 100. I can just take 100 or 1 and subtract our 49, our 27, and our 20. And I'd get that there is a 4% chance of having an AB type. Maria has a B blood, has type B blood. She can safely receive transfusions from people with blood types O and B. What is the probability that a random chosen Black American can donate blood to Maria? So what's the probability of being O or B? Well, it would be the probability of O plus the probability of B. There's no overlap. You can't be O and B, so we wouldn't have to subtract anything. We'd have the 0.49 plus the 0.2. Okay, that's easy enough. Moving into a sample for continuous data. Sometimes we want to use a curve, a density curve, such as a normal curve, to display our probability distributions. Okay, so here is our distribution that is normal. Sometimes a curve will do a good job, and then the areas would represent the probability. Here is an example, and we've done this before when we talked about normal distributions with the percentages being like the percent of our population. Well, it just kind of goes along with the fact that that would also be the probability. Let me just show you a couple examples. Opinion polls of teens have determined that 50% of them approve of legal gambling. Suppose that we took a sample of 501 teens and asked them the sampling distribution at the right shows the probability distribution. what does it mean? Well, it appears from the sampling distribution that the mean is 0.5. The standard deviation, if this is one standard deviation, this would be 0.022. Now, we are told there is only a 2.5% chance that our sample will have at least what percentage approving of legal gambling. So 2.5% chance. Now, we remember the 68, 95, 99.7 rule, where it says that we are 2 standard deviations out, 95% of our data would be in there. That means 2.5% would be in this tail, and 2.5 would be in this tail. There's only a 2.5% chance that our sample will have at least what percentage? Well, if we talk about being up here and this value, so 2 standard deviations that grow above the mean, then there's only a 2.5% chance that we are going to be greater than that value. Here, if we're down here, that would mean there would be a 2.5% chance that we'd be less than the value. We'll have at least what percent? So we're talking about this value up here, where, you know, our value, there'd be only 2.5% of our population being greater than 2 standard deviations above the mean. Okay, so that's the whole 95 rule. Now I take that 0.5 and I add 2 of my standard deviations, which is 0.044, so that'd be 0.544. Okay, so there's only a 2.5% chance that we'd have, you know, 54% of our teens would approve legalizing gambling. Part D, what is the probability that more than 2/3 of our sample approve of legal gambling? So we got 66.6667%. Now we have that as an observation. We will turn that into a z-score using our familiar formula, observation minus the mean divided by the standard deviation. So I'm going to take that 2/3, subtract the mean, which in this case happens to be 0.5, and divide the standard deviation, which is 0.022. And I get a z-value, which is 2/3 minus 0.5 divided by 0.022, and I get 7.57. Okay, that's huge. Now we want to figure out what the probability that we have a greater than that many standard deviations of the mean. We're looking at this area up here. Now we know that for normal CDF we'll use 10 in our calculator as our max and -10 as our min. I'm going to plug in normal CDF from 7.57 to 10. We're going to get a value that's extremely small. This is not a very good question, unless my standard deviation is wrong, but 0.5222 minus 0.5 is 0.022, so my standard deviation is not wrong. So I go dister, normal CDF is 2. I start at 7.57. I go up to 10, and I should get an extremely small value. There's like a 0.000, almost close to 0% chance. Okay, but that's the idea. We take our observation, turn it to a z-score, and then when you find our area, our answer is a probability rather than a percentage. So the question is not percentages anymore, it's a probability. Let's look at this question. Hopefully this will be a better question. The weight of a 16-ounce bag of chocolate chip cookies can be viewed as a random variable with an approximate normal distribution with an actual mean. So the actual weight is 16.1 ounces and the standard deviation is 1 ounce. Okay, this is good so far. So we're not talking about percentages. We have an actual, value, and that's okay. What is the probability that a randomly selected bag will be underweight, which is less than 16 ounces? I think about my curve, and this is 16.1. Try to figure out what is the percentage down here. And that would be the probability of a bag being less than 16 ounces. I'll turn 16 ounces into a z-score, observation minus the mean, divided by my standard deviation. Gives me -1. I can do that in my calculator, but you can see it'd be negative 0.1 divided by 0.1. 16 minus 16.1 divided by 0.1. Okay. And I want to figure out what is the percentage underneath one standard deviation below the mean. So in normal CDF, I would go from negative 10 to negative 1. You can also use the 68, 95, 99.7 rule. And we get that it's around 16%, 15.86%. Okay. B, what is the probability that a randomly selected bag will be over 16.2 ounces? Well, let's figure out this. If this is 16.1, what is 16.2? 16.2 is going to be one standard deviation greater than the mean, just to confirm that. Observation minus the mean divided by the standard deviation. And we get 1. I'll go normal CDF from 1 to 10, and I'll actually get the exact same value, 15.86%. Think about it, it's just symmetrical with your normal distribution. From negative 10 to 1, negative 1 will be the same as from 1 to 10. And there we go. What is the probability that a randomly selected bag will be between 15.75 and 16.25 ounces? So think about our normal curve, this being 16.1. We're looking at between here and here. So what is this area here? So we're going to find the two z-scores, and we'll just normal CDF between the two z-scores. Okay? Find the z-score for the 15.75. 15.75 minus 16.1, which is my mean, divided by my standard deviation. This gives us, it'd be minus 3.5, it looks like. Negative 0.35 divided by 0.1 is minus 3.5. So pretty far below the mean. And the z of 16.25 will be 16.25 minus 16.1 divided by 0.1. Let's do that math. It'll end up being 1.5. Confirmed. And then to find the area between the two, I'm going to go normal CDF. Negative 3.5 as my low, 1.5 as my up. Should be a very large percentage, which means it's very likely that I'm going to get a bag of potato chips between 15.75 and 16.25 ounces. Second dister, normal CDF, negative 3.5 as my lower, 1.5 as my upper. And I get 93 point, let's just say it's 3. Okay, so this is probability distributions, either discrete distributions where we can add up the individual events to be 100, or non-discrete infinite distributions. However, the area being under the distribution would be 100, like a normal distribution, which we're used to. Okay, that is the last set of notes, very simple.